What's going on, seventh grade? This is Mr. Bradford again. A few things before we start off. One, if you have not finished the work from last week at this point, which should be Monday the 5th, by the time you're watching this, don't worry about it. There are a couple things, we're all figuring this out together. A lot of the kids that had like the USB drives didn't even get the right video. So that obviously would make it hard to understand how to do the assignment. So again, if you haven't done last week's assignment at this point, just don't worry about it. We'll call it a wash. We'll get on with this week's. Um, Another thing we need to talk about is the Zoom meetings I'm doing are I'm going to say optional, but let me explain. I'm not going to be teaching on the Zoom meetings. I won't be like having class. It's not going to be where I'm instructing. It's just if you have any questions, we can speak face to face. And so there's less confusion, less loss of meaning in, my responses. So again, the Zoom meetings aren't something mandatory that you have to show up to. It's just a way for us to speak face to face. So last week we did what was supposed to be kind of like an introduction to see how much you guys know. Not really appropriate for this teaching format, I would say. So this week I found a video. We're going to be watching it, then I'm going to talk a little bit more about some stuff that I think the video left out. And then for the assignment, we're going to just answer a couple questions. So this video is pretty good. It misses a couple things, but I feel like it's a good baseline. So we're going to watch this.
Now everybody stand back.
Is it gonna explode or something?
It might blow your mind, Amar, but no, it won't explode.
Gosh darn it.
Or maybe it will explode.
Yeah, all right.
Right, boy.
Ooh.
You see, when I mixed the substance in the beaker with the substance in the test tube, these were my reactants. A chemical reaction occurred. And when a chemical reaction occurs, new substances are formed that weren't there before. These new substances are called the products. Pretty neat, huh?
Not as neat as that explosion you almost promised.
Can we see another chemical reaction?
Why, certainly. In fact, there's one happening right behind me.
That's the bike you ride to school every day?
The one and only.
Why is it so brown?
Well, the non-scientific answer is I had to start using a hand-me-down after my last bike got run over by a plantain truck. Long story. Talk to me after class. But the real answer is that the metal on this bike is undergoing a chemical reaction that is slowly producing rust. See the orange streaks?
Do we?
Speaking of orange streaks, hello!
Well, hey, Bunsen, how's it going? You enjoying my lesson so far?
It's fabulous! Just like your taste in original Frankel prints. But you might be surprised how challenging this can be for students.
Well, I'm trying to keep things simple by not getting into the nitty-gritty just yet.
But that nitty-gritty is where it's at. Students tend to have a better understanding of chemical reactions when they're asked to explain what they see in terms of atoms and molecules. This can begin with teaching the concept of a substance. So instead of just saying that metal is producing rust, you might explain what makes up that metal. One of those things is called iron, made up of iron atoms. Give it a whirl.
Okay, class. Let's see if we can, like my spinning instructor says, dig deep and put the pedal to the metal. Who can tell me the difference between an atom and a molecule? So, as I was saying, the metal making up this bicycle contains iron, which is made up of iron atoms.
Who are you winking at?
These atoms can undergo a chemical reaction that produces rust. I think they're really starting to get it now.
We're off to a grade A start, but we might be getting a little ahead of ourselves. Let's take a peep inside Amar's noggin.
These atoms can undergo a chemical reaction that produces rust. Okay, for the record, I'm much more graceful than that.
See, Amar is just starting to understand what happens with atoms in chemical reactions. But, as you can see,
Where'd those oxygen atoms come from?
well, he is right that rust is made up of more than just iron. But where did he think those atoms came from?
I realize now that I wasn't very specific earlier. I should have said, the iron atoms in this bike combine with oxygen molecules from the air around us to produce rust. I think Amar is on a good path, but I've seen enough to know that doesn't mean all my students have landed in the same spot.
Exactly the point I was just about to illuminate. Why don't we dive into Justine's perfectly shaped melon to see what she took from that?
The iron atoms in this bike combine with oxygen molecules from the air around us to produce rust. Oh, come on. Just for the record, my nickname in spinning class is the Viper. See, Justine's already thinking on the molecular level. Rust atoms? That's not a thing.
Neither are wallet-sized hadron colliders, but that didn't stop me from pre-ordering one just in case. Many students who hear about two substances combining imagine that they become something totally new, made out of different types of atoms.
I noticed that. Perhaps I can walk them through the chemical equation.
Whoa there, Speedy McQuickerson. That's some of the fastest chalkboard riding I've ever seen. Was that chalk dust or smoke?
Not too bad, huh? I feel like this will really help them understand what's happening.
Reactants over here, you got iron and oxygen, the gas, and it reacts together to form the product, which is rust.
Not so fast there, the Viper. I mean, talking about the chemical interactions from a molecular standpoint is a good start. And seeing the interactions written out can help, but it's definitely an abstract concept, and those symbols can be confusing on their own.
That's your solution? Marshmallows?
When aren't they the answer? Seriously though, having students use concrete visual models helps them to reason through how atoms rearrange into different molecules. You don't have any food coloring, do you?
Not on me.
Oh well. Not the most aesthetically pleasing, but it'll do. Now, using these brown marshmallows to represent iron atoms and these three red pairs to represent oxygen molecules, we can help show students how rust is formed. Breaking molecules apart and using the atoms from the reactants to build new molecules can really show students what chemical reactions are all about. And as a fun bonus, it also reinforces the law of conservation. Let me show you. Learning with concrete models can steer students into only building products from what they started with. Nothing more, nothing less. It also
Okay, so the law of conservation, he's showing you how, this is rust, right? He's quote unquote holding rust.
reinforces the law of conservation.
So there's rust. Didn't really go into the law of conservation of matter so much. So the law of conservation of matter, according to the law of conservation of matter, matter is neither created nor destroyed. So we must have the same number and type of atoms after the chemical change as were present before the chemical change. So rust, the rust isn't just coming out of nowhere. It's not being created from nothing. It's the oxygen and the iron are just rearranging themselves to look and different and make rust, right? Another example is like burning a piece of paper. Burning anything is always a chemical reaction. And so you burn a piece of paper and you have a pile of ash. Well, there's not like less of anything. It's just, bits of the paper get released into the atmosphere, and then you got the leftover, which is right there. But it's the same amount of stuff. Conservation of matter, big one right there.
Or nothing less. You don't happen to have any chocolate or graham crackers, do you?
It's with the food coloring.
Oh well.
Marshmallows seem like a useful and fun way to get my students to reason through these chemical reactions. But there's something about the atoms of that rust molecule sitting in a straight line that feels like it could be misleading. Rust isn't arranged like a falafel kebab.
Every physical model is going to have its limitations. The classic ball and stick models can certainly help give a better sense of how the atoms within a molecule are arranged geometrically. So when you're ready to talk about the details of chemical bonding, use that one too. Variety is the spice of life.
And I'll make sure to point out the strengths and weaknesses of a given model. It's good for students to be reminded that models are imperfect.
Well, not all models.
Mm-hmm.
Of course, you can reinforce these concepts of conservation and rearrangement by having students clearly define the system being considered. A common source of confusion is that all the reactants may not be obvious or accounted for. Like earlier, when Amar was viewing the system as consisting of only the bicycle. Help students reason that the air is made up of molecules and that those molecules can be reactants while also having them get in the habit of clearly defining the system they are considering.
Your suggestions are spot on as usual, Bunsen.
I'm glad you could match my enthusiasm. Fire pun. Hi-yo!
It might be time to dial back on the gas, my friend. But first, are there any more big misconceptions I should be on the lookout for?
Does hexane contain 14 hydrogen atoms? Of course, silly. One more pervasive misconception is the idea that chemical reactions are one-way streets, that all are completely irreversible.
Yeah, I think I know a colleague who still believes that. He shall go nameless, but it rhymes with Mr. Smolberg.
Ooh, you are bad, bad, bad. I love it.
I know. A lot of teachers still use the notion of irreversibility to explain the difference between chemical reactions and changes in state or phase. The erroneous rule is that physical changes are always reversible. A gas can go back to a liquid and back to a gas again, while chemical changes never are.
It's time we kick that rule to the curb.
Amen.
So, just taking a pause there, they're saying that people used to think that chemical reactions could not be reversed. Like once it chemically changed, there was no going back. But now people think that there are some that are reversible. Just to make that straight and clear.
I think the misconception that chemical reactions are always irreversible also stems from the fact that many reactions are referred to in classrooms as, quote, going to completion. Ugh. In reality, most chemical reactions have a balancing point, not an end point. Imagine you're at the beach. Some people are going to be lying out in the sun or playing volleyball. Others are going to be in the water, swimming or splashing around. Sometimes people on the beach will get into the water, and some from the water will come out to dry off. But overall, the ratio of people on the sand to those in the water is about the same. It's not frozen. The system is in constant flux, but the overall picture is stable.
I gotta say, Bunsen, you were really...
On fire today?
I was gonna say helpful, but sure. Now, if you don't mind, I'm gonna get back to my students, but first... If you don't mind.
Oh, of course not. You want a golden brown or cremated? I prefer mine crispy exterior with gooey center, but some people like a uniform squishiness. Others like it burnt like a hot dog on the 4th of July. To discover more about how kids learn science and the types of misconceptions they have,
All right, so let that go away. So this is a pretty good video. I had to stop and talk about the law of conservation of matter. Another thing that I thought it kind of missed out on is how do you know if a chemical change has occurred? So we're going to go through this right now. I'm just going to read it for you guys. Elements, atoms, and compounds are often too small for you to see individually. So how can we know if a chemical change has occurred? Well, first of all, a chemical reaction takes place when one or more substances are changed into a new substance. This means that the chemical composition of a substance changes. It is important to remember that matter is neither created nor destroyed. Conservation of matter right here, right? In a chemical reaction. Instead, a substance is simply rearranged to form another one. Remember the marshmallows? They're just rearranging. This new substance, excuse me, can be in any state of matter. Solid, liquid, gas. Now you guys did that. Here are the 5 signs of a chemical change. Color change. You've probably seen this kind of change before. Blah, blah, blah. Rust, right? Rust is an easy one. It goes from a regular iron color to that orange, distinct, everyone knows what rust looks like thing. Forms a new compound called iron oxide. Indicates a chemical change. Temperature change. So when energy is either absorbed or released, it is indicative of a chemical change. Fireworks are an example of a chemical change that produces a temperature change and emits light. Fireworks contain fuel and an oxidizing agent. As the oxidizer breaks down the fuel, it releases an enormous amount of energy. Some of this energy is released as heat, so remember not to get too close. Precipitate formation. When 2 salts are mixed, it is possible for a solid substance to form and precipitate out of solution. Precipitate out of solution. This means that if you start with 2 liquids and then see a solid substance in your beaker, it is clear evidence of a chemical change. So you're mixing 2 liquids and then that creates a solid substance-y thing in the bottom, chemical change. Precipitation reactions are very important in making sure water is safe for human consumption. Water purification facilities make use of the fact that they can add a chemical to the water which will react with an impurity in the water and precipitate. Then the now pure water can be removed from the solid which contains the impurities. So that's a bit of a thick concept right there. I don't know how many of you guys keep fish tanks, but there's like our water's like chlorinated, right, to make it safe for drinking, but that's not safe for fish, so you put a dechlorinator in your water so to make it safe for fish. That's kind of the same thing as like that example right there. You put the dechlorinator in your water, and what it does is it collects on the chloride atoms, I guess, I don't know, and turns it into solids which sink. So instead of floating around the water, they're just at the bottom, and that makes it safe for fish. Gas production. Production of gas is a clear sign that a chemical change has occurred. A quite delicious example of that is baking a cake. So you're baking a cake and all the things are being cooked and reacting together and you're smelling it. That's a chemical reaction. Would water boiling be an example of a chemical change? Well, not really. Hang on. Yeah, it's important to keep in mind that even though the phase of the water is changing, the chemical structure has not. So there's still like H2O atoms are just like, like in the air or whatever. So that's more of a physical change. Light emission. Is a light bulb going on by now? Pun. There are many reactions that produce light and allow you to see that a chemical reaction has taken place. One example that you may have witnessed firsthand is the reaction of a light stick. So you have the light stick that has a little glass inside that you break, and once those 2 things mix together, it forms light. Perfect example of the chemical reaction. When you bend the light stick and break the small glass vial on the inside, you initiate a reaction between hydrogen peroxide and phenyl oxalate ester, which results in the emission of light. So, color change, creation of heat, gas, precipitate, light. 5 basic ways for you to just know that a chemical reaction has occurred. Maybe next week I'll do like a sheet with like changes, and you'll have to decide whether they're chemical reactions or just physical reactions. But for now, all we're going to do is this Word doc is going to be in your Google Classroom, and I just want you guys to, however you can, whether it's downloading this Word document and editing it with the answers and then returning it in, whether it's sending a picture of a piece of paper that you wrote the questions and fill out the answers. You can send me pictures on email. Just any way you can turn this in, just go ahead and do that. So that's about all I have for you guys. Let me know if you have any questions. You guys still have my email. And until next week, I'll talk to you guys later.